today we're finding out, is it possible to completely fill
The Klein bottle.
Klein bottle?
The Klein bottle was first imagined by a mathematician named Felix Klein, who wondered what would happen if you take two Mobius strips and sew them together on the edges. The result is a Klein bottle. You can see that if you follow an edge, the outside becomes the inside. According to topology, the Klein bottle has no volume. But if it has no volume, then what if we try to fill it with water? So when we try to fill it up, we can get it this far and it's already full. Then you have to tilt in the water. It fills it up a little bit at a time. Well, if we just pour some water in it, then you can see that we're not going to be able to get the air out to get the water in. So you can see you're always getting blocked by trying to pour more in here. When I try to let the air out, then I pour out the water. But I have a better way to fill a Klein bottle. I'm going to stick it in my vacuum chamber and suck out all the air. Then when I let the pressure back in, it will force the water up into the void in the bottle. All right, in order to do this, I'm going to try to stick the Klein bottle down so it won't.
How do you have your own vacuum? Jesus, man, this is fucking mental.
Float. Now I'm going to pour some water around it. Now we're going to try to get that water inside the Klein bottle. Okay, turn it on. 3, 2, 1. So it's immediately bubbling because the air is expanding from the Klein bottle coming out the bottom.
All right.
So all that bubbling is coming from the air inside the Klein bottle. So we're trying to get the inside of the Klein bottle to be as rarefied as possible. Okay, let's see what this looks like now when I stop it. Okay, let in the air, and it should suck right up into it.
Oh my god.
Here we go. Whoa, it's already going in. That is awesome. Fill it up.
I'm in shock.
Didn't quite fill it all the way up. Okay, let's turn the vacuum back on and let this go for a while longer then.
Let's do this. This is just so crazy, man.
Okay, now we're taking this smaller volume of air and rarefying it again. Okay, do it again.
Yeah. There's little bubbles in that water. Is it filled? Has it done it? Not quite.
Almost.
Gone.
A fully filled Klein bottle.
That's actually insane.
So I was able to fill a shape with no volume. Now at this point you may be asking why I would say that the Klein bottle has no volume.
See, I disagree, right? You've not filled a shape with no volume. What you've done is you've created a shape with volume because you're holding the water like that, right? So no matter what it is, right, the top of the water, where the water line is, that is the edge of the volume, so there's always volume within it. So I don't know, I don't agree with your point there, I'll be honest.
Because in order to have a volume, you have to divide the inside world from the outside world. For example, this sphere has a volume.
So this is what I'm saying, this is what you've done by filling it with water, or the blue liquid or whatever, you've created the gap between the inside and the outside world.
There's a world outside the ball and a world inside the ball. And no matter how I stretch or manipulate the shape, there will always be a volume to it. But let's look at the Klein bottle. Where does the outside world end and the inside world start? There's no fine line or edge to divide it into an inside or an outside. Now the fact that the Klein bottle has no volume isn't actually that special. For example, this beaker here has no volume either. There's no division between the inside and the outside world. We can artificially define the inside of the cup as anything below this line here, but that's just some arbitrary definition of the inside that we're used to living with because we know that when we pour something in it, it'll stay there because of gravity. But in topology, this cup is no different than a flat disk. Now this problem with shapes having a volume was first realized in 2 dimensions by the mathematician Camille Jordan. He realized that there's no rigorous mathematical proof to tell the difference between a curve that encloses an area like this one or a curve that doesn't like this one. He went on to create the first proof of the Jordan curve theorem, which is why it's named after him. And it's actually one of the more difficult proofs out there. For example, we can look at these 2 lines and instantly know they're different because there's one that encloses an area and one that doesn't. It seems obvious.
It is.
But in order to prove it, this is what it takes. Mathematical papers use something called a lemma. A lemma is an intermediate proof that will be needed later to prove what they're trying to ultimately prove. So this paper publishes the proof of the Jordan curve theorem. It shows lemma 1, lemma 2, lemma 3, then lemma 4, and then it finally gets to the actual proof. This is all to prove what we can instantly see with our eyes. So sometimes things are obvious to our eyes that isn't obvious in mathematics. But some interesting results happen once you start to understand these curves. For example, a simple closed curve like this one means that if you draw a point inside the curve, no matter how it moves or stretches the shape, it can't get out. Now for this example, it's easy to see that the point is inside the closed curve. But what about this closed curve? Is the point inside or outside this curve?
It's quite difficult.
Well, since we now understand these curves, there's some rules that we can follow. If you draw a line between the point of interest and another point that we know is outside the curve, then you can just count how many times it crosses the curved lines. And if it crosses it an even number of times, it's on the outside. If it crosses it an odd number of times, it's on the inside. Now back to our Klein bottle. From the start, notice that I called this a physical Klein bottle. That's because a true Klein bottle doesn't actually exist because it needs 4 dimensions to be a real Klein bottle. So this is a 3D immersion of a 4D Klein bottle. A proper Klein bottle doesn't intersect itself, but it actually lifts this portion into the 4th dimension, so it doesn't intersect itself. You can see in this 4D visualizer of 3D slices what it would look like. This is the self-intersecting Klein bottle in 4D, seeing 3D slices of it. And this is a non-intersecting Klein bottle. We have an extra dimension so it can move around itself so it doesn't have to self-intersect. So a true Klein bottle can only really exist in 4 dimensions. So in 3 dimensions, a Klein bottle is just a really fancy cup that you need a vacuum chamber to easily fill up.
Alright, this is my head's boggled. I think is the term, but I'm really struggling to understand this. God. But it is possible to completely fill a Klein bottle. That's what we've learned. If you decide that filling a Klein bottle means it's full, create a volume for it and you can fill it. That's what we've learned.